Hi, my name is Lindsey Fasolo, and I did my final project on virtual and cache memory. A little introduction. In 1956, German physicist Fritz Rudolf Gunz first developed virtual memory, and a fact that IBM personal computers did not have virtual memory at first because they believed that personal computers would never need the amount of memory um, that would go outside of RAM. Virtual memory allows for address spaces to be shared by several processes, and more programs can run concurrently than can fit in physical memory. So one of these techniques to use for virtual memory is translation, in which addresses are translated from virtual memory to physical memory. After the program is executed in RAM, the data is stored into that program and then returned to the program's location in virtual memory, which is where it resides permanently. It's only in RAM temporarily, so to only keep the data in RAM wouldn't be beneficial because then it wouldn't be able to be transferred back. Memory can also be stored on a disk, and this is also saved in the translation table. So the translation table shows how it gets from the address that it's at in virtual memory to the address that it's at in physical memory. And also, if it's not in physical memory at all, then it'll say disk in the translation table. Another technique to use for virtual memory is paging. First, however many bits that make up the offset are loaded directly from virtual memory to physical memory. There's no translation needed. If the physical memory is full, then a page swap needs to be made, which will be explained later. And pages are only brought into RAM when they're needed, which is known as demand paging, kind of like supply and demand. If that page is needed at that certain time, then it's loaded in. If it's not needed, then it doesn't need to be loaded into RAM. And a typical page size is 4 kilobytes per page. Some page replacement algorithms that are used to do the swapping are the FIFO, which is the first in, first out algorithm. And just like it sounds, the first page that was loaded into RAM will be the first one removed when it's the LRU is the least recently used page, is the one that is removed. This works similarly. It uses a counter to store the clock time. So when that page is called upon, the clock will be stored in a counter. And then the clock that is the least number of time will be the one that's removed. Optimal algorithm removes the pages that will not be used for the longest period of time. And then the LFU and MFU are the least and most frequently used. So they store a counter, and every time that page is called, that counter is incremented. And the least frequently used will remove the page that has the lowest counter. And most frequently used believes that the one that is the least frequently used cannot be removed because it would have just been brought into main memory and is still important. Thrashing is something that can occur when using virtual memory, and it occurs when the number of pages allocated for a process are not enough pages to run that process. So if you need 5 pages to run a certain process, then if you only have 3, then it will constantly be trying to enter all 5 pages at the same time, which cannot happen. So this happens, like I said, if the working set is less than the amount of RAM that's available. Page faults will continually occur because the pages needed are swapped out, and then once they're swapped in, then one of the other pages that's needed next will be out, so it'll page fault after that, and this slows down the CPU exponentially. The other topic on my paper was cache memory. Cache memory is located directly on the chip, and it was created to solve the problem of the slow interaction time between the CPU and the RAM. There are 2 types of cache memory cache and disk cache. Memory cache uses static random access memory, which is opposed to dynamic random access memory. Static random access memory is used because it's much faster, and that's the point of cache memory. There's also 3 levels. Level 1 is the smallest, fastest, and it's located in the CPU. Level 2 is medium size and speed, and it's located on the computer microprocessor. And level 3 is the largest, slowest, and it's located in main memory. Levels 1 and 2 are used individually by certain processes, but all processes and cores will share level 3. There's only one level 3 cache in each system. So the cache replacement algorithms are similar to the page replacement algorithms. There's first in, first out, least recently used, and then Bilatti's algorithm is the equivalent to the optimal algorithm for page replacement. It references the future, which, like I said before, isn't feasible. The pseudo LRU is similar to the least recently used algorithm, but it only needs 1 bit per cache item. There's random replacement, which exactly like it sounds, will replace something randomly. It doesn't take into account how many times it's been accessed or how recently it's been accessed. It just picks one of the pages at random and takes that one out. And then there's segmented least recently used, which there's 2 cache segments, probationary and protected. Protected has a set size, and then in each one of those 2 segments, information stored from most recently used to least recently used. If it's in probationary and it gets called upon, it gets moved to the most recently used in protected. And then because the protected is a set size, when it becomes full, the end of it will be then taken out of memory completely, and then it'll go back in.